Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue looking at plate tectonics. So in this video we're going to be looking at transform plate boundaries. So this is going to correspond to section 3.7 of your textbook. So transform plate boundaries are rather straightforward things. It's simply where we have two pieces of crust or two plates moving past each other. That's it. No crust is being made. No old crust is being destroyed. The plates are just simply moving past one another. That's sometimes why transform plate boundaries are also referred to as conservative plate boundaries, because the crust is conserved. Nothing's being made or destroyed. So transform plate boundaries aren't particularly complex things. Now, they do, however, help us to answer a question which we started talking about right in the first presentation. If you remember, when we were looking at the seafloor, we started to notice how the ridges that run down the middle of the ocean have a rather distinctive zigzag shape to them. They look almost like they're steps. So the question is, well, why is this? Well, it just so happens that divergent plate boundaries are not operating at the same speed everywhere. So if I have a divergent plate boundary, some parts of it will be creating new oceanic crust quite quickly, and some parts of it will be creating new oceanic crust more slowly. So if we were to look at this diagram here, this would represent our divergent plate boundary. So here's our zigzag. We can see it's coming down here, there, 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 there and there. And these regions here where we have a gap, this represents our divergent plate boundary when new crust is being made. Now, as I've discussed, some sections of this divergent plate boundary will be making crust quite quickly. Some sections will be making crust more slowly. And so this means they're moving at different speeds. And because they're moving at different speeds, it means they begin to shift position relative to each other. Now, this means, therefore, that because they're shifting position, we need something that's going to link these segments of the divergent plate boundary. And the thing that's going to link them are the transform faults right here. So you'll notice that here's our divergent plate boundary where new crust is being made. So this is the new oceanic crust here. It's being pushed westwards. So that obviously means it has to move past this piece of oceanic crust here, which, comparatively speaking, is moving eastwards. And so this has to be our transform fault right here. So you can see we're going divergent plate boundary, transform plate boundary, divergent, transform, divergent, transform, divergent. And so this coexistence of the divergent and transform plate boundaries together helps to explain this zigzag pattern that we see associated with mid-Atlantic, with mid-ocean ridges. And we can see it here in this diagram. Here are our divergent portions where we have new oceanic crust being made. There's one there, there's one there. And we can see these two segments of the divergent plate boundary are connected by this transform fault here, which is allowing this piece of oceanic crust to go that way and this piece of oceanic crust to go that way. And it's letting those pieces slide past each other without any significant fuss. So here we go. If we look at the South Atlantic again, we can really begin to see this zigzag pattern we were just talking about. So if we look, we can see as we come down, we can see the steps in the divergent plate boundary quite clearly. So these segments here, which are running approximately north-south, those are the divergent segments where new oceanic crust is being made. Linking these divergent segments together are these transform faults. So right here is going to be an area of divergence where we have new oceanic crust being made. So that's a divergent plate boundary right there. We have another divergent plate boundary right here, or another segment of it, should I say, and we need to link them together. So here we have a really big transform fault right there, which is linking these segments together. And you can see these transform faults because we can see the traces of them there on the seafloor as well. And you can see another one here. So here we have our north-south orientated divergent plate boundary. Here it is again down here, and these two segments are linked together by a transform fault right there. So, as you can see, these divergent plate boundaries are a mixture of divergent segments where new oceanic crust is being made and the transform faults that link them together. Once again, here's the diagram we just saw a second ago. There's our divergent plate boundary, and here is the transform fault linking them together. So this is where most of the transform plate boundaries are actually going to be found. They're going to be associated with divergent plate boundaries. Now, if we look here in the Pacific Northwest, we actually have a situation which is slightly different. Now, here is the Cascade subduction zone. So this is going to be Northern California here, then Oregon, Washington State, and then up into southern British Columbia. Now, you'll notice that here we have our zigzag pattern. So here we have a spreading ridge, okay, where new oceanic crust is being made. The yellow portions are the divergent portions where the crust is being made, and that means these green segments here are the transform faults linking the divergent portions together. That's relatively straightforward. We just saw that in the South Atlantic on a much larger scale. In terms of the new oceanic crust being made, it's being subducted underneath North America here. So here's the Cascade subduction zone. So there's a trench that runs along here that shows us where the subduction is taking place. Now, the thing that we'll notice in this diagram, though, is that we also have the San Andreas fault down here and the Queen Charlotte fault right here. I should point out the Queen Charlotte fault actually continues all the way up into Alaska, but at the Alaska-Canadian border, it stops being called the Queen Charlotte fault and it gets renamed the Fairweather fault. So why is this situation slightly different? Well, these are the kind of transform faults we've seen before, associated with divergent plate boundaries, but the San Andreas and Queen Charlotte faults are slightly different. So these are examples of transform plate boundaries. So in the case of the San Andreas fault, we have the Pacific plate wanting to move in an approximately northwesterly direction. And so this obviously means it wants to go that way, because there's a subduction zone located up here off to the north. Now, this means, therefore, that the Pacific plate has to move past the North American plate. And it does this by having transform plate boundaries here, which we see as the San Andreas fault and the Queen Charlotte fault. So in the case of these two plate boundaries, these are examples of where a transform boundary is not associated with a divergent boundary, but it's just there to accommodate the movement of two plates. So in this case, the Pacific plate wanting to move past the North American plate. So don't think that all transform plate boundaries are associated with divergent plate boundaries like we have here. I'm going to be honest, most of them are, but there are also examples where we have true transform plate boundaries which allow pieces of crust to simply move past each other without having to have any crust made or destroyed. Okay, that's it for this presentation. Thank you for watching. Take care.